Three-dimensional worlds made with Three.js routinely contain some kind of movement. This could be the movement of individual objects in a scene, camera movements, or movements caused by user interaction. Each time there's movement in a 3D world, the existing screen image must be rapidly re-rendered to reflect how the scene has changed. And this stream of new frames must be delivered with consistent timing regardless of their size, resolution, or the screen refresh rate of the device displaying them. Earlier videos in this series showed you how to set up a Three.js world and hype using JavaScript ES6 modules. This modern approach is helpful because it divides the code for your 3D animation into small interacting parts instead of one large JavaScript file. This makes your project more manageable, especially as your animation grows in size and complexity. Eventually, we elaborated this approach to include an animation loop and used it to put various shape primitives into motion. An animation loop is code that runs once per frame and is used to update and continuously re-render each scene. To give the impression of smooth movement, this kind of loop needs to generate 60 new frames each second, which can be quite challenging if the scene has a lot of elements or complicated shapes that require significant amounts of processing to redraw. In an earlier video, I implemented this animation loop without much explanation. Now, in this video, I'll explain how this code works in more detail and highlight why this is a useful way to set up an animated scene. In particular, I'll explain how Three.js uses a function called setAnimationLoop to coordinate this process and how that differs from traditional browser animations that commonly use a function called requestAnimationFrame. We'll also consider another function built into Three.js simply called clock. This function allows you to render frames at a frequency of your choosing and in a manner that's independent of the device's refresh rate where it's being displayed. Finally, I'll show you how to measure and display your project's frame rate during development using the JavaScript performance monitor that ships with the base Three.js package. This indicator can be a particularly helpful troubleshooting tool in situations where you have a complicated scene or one that requires a lot of processing to render the objects in your 3D world. So, if that sounds interesting to you, let's get started by re-examining how our project is structured and how we went from rendering a static scene to an animated one with many moving shapes. This is our project structure so far. You can see how we've organized things in a way specifically designed to use JavaScript modules. We did this in the main.js file that we load manually in the head of the Hype project. This script file is configured with a module type, which means that its loading is delayed until everything else in the project is in place. You need to manually add this to Hype's head because by default, Hype will designate the script file type as text/JavaScript, which will give an error for projects utilizing code split into modules. Loading order is important here because we need a canvas ID from Hype to hold our 3D world. Hype's setup has to be finished before this ID is available. The fact that this top-level main.js file has a module designation also means everything else in the project can be imported as an ES6 module using modern JavaScript syntax. Distributing code across many small files like this, rather than a single large one, is the big advantage of ES6 modules and why it is now standard practice in the JavaScript world. You can also see in this figure how our 3D world is constructed in its own separate module called world.js. This module pulls in code from many different parts of the core Three.js package and configures each element of this world in its own separate JavaScript file. This is handy from a programming perspective because it clarifies where things should reside and divides up individual components in a logical way. Along with these core Three.js features, our project also pulls in code from some auxiliary Three.js modules. You can see this in the top left of our diagram, where we incorporate a set of orbit controls and a performance monitor. So with that brief review, let's examine how we went from rendering a single static scene to an animated one. When I first made this project, I used the renderer.render method to draw static 3D objects in a scene. To set this up, I made a separate renderer.js module that pulled in rendering code from the base Three.js package. That code looks like this. This module's createRenderer function was then imported into the main world.js file, where a renderer object was created. The code for that looks like this. Finally, we fed the scene and camera as arguments into this method, which then output a single still image to the HTML canvas element I'd previously set up in Hype. That process looked like this. This is a good starting point, but a slightly different approach is needed to make an animation loop that continuously re-renders the scene. Another method associated with the renderer we created in renderer.js is called setAnimationLoop. This method was also pulled into our project when we incorporated the original WebGL renderer from Three.js in this step. This WebGL renderer is the low-level JavaScript API that renders interactive 2D and 3D graphics within any compatible web browser. Three.js is built on top of WebGL and hides its underlying complexity. This is a good thing because WebGL is very complex, and it's difficult to accomplish even the most straightforward operation without pages of code. The renderer setAnimationLoop method does a lot of the heavy lifting for us by intelligently scheduling frames in sync with the refresh rate of your monitor and will smoothly reduce the frame rate if your hardware can't keep up. Under the hood, the setAnimationLoop method still uses the browser's requestAnimationFrame method. However, with setAnimationLoop, there's some additional magic to ensure this loop will still work as browser technology evolves in the future. In particular, this includes supporting features that allow virtual reality and augmented reality scenes. While this method is considered a best practice, it's helpful to know that it was only recently added to Three.js, and there is a good chance that you may still see older Three.js examples and tutorials that use requestAnimationFrame directly to set up this kind of loop. To set an animation loop in motion, we need to incorporate the renderer.setAnimationLoop method in our project. We'll do that next. The logic to support our animation loop is contained in a separate module called Loop.js. You can see the code for this module here. We import this module into the main world.js module just as we've done before, using code like this. While the code in Loop.js seems a little intimidating, let's examine it part by part and try to understand what it's doing. In fact, this module contains just one main class simply called Loop. JavaScript classes like this are just special functions that act as templates for creating other objects. We've already used this approach in world.js. Each class has a key method that creates and initializes objects for that class. This method is called a constructor and each class can only have one constructor. You can see what the constructor for this class looks like in this code block. This class has other methods, including ones to start and stop our animation loop. It is within these methods that we apply the setAnimationLoop method we mentioned earlier. You can see that here. Within the start method is also where we render the first new frame just as we did when creating a static scene. There is one final method in this class called tick, and this is where things really come together. We'll talk about how this function works next. Each time our loop runs, we want to increment the position of each object by a small amount and re-render our scene. We could do this one object at a time, but that's a lot of things to keep track of. Instead, this tick method tells every animated object to tick forward one frame. In theory, you could describe each small movement for each object inside the tick method itself. Such an approach is often called a centralized design pattern. This works fine, provided there are only a few objects, but it quickly becomes unruly as the number of objects grows. Alternatively, you could specify these movements inside the module that created them in the first place. Controlling movement in this way is termed a decentralized design and is generally considered a superior way of doing things because it scales better. Using this latter approach simplifies the loop class but requires keeping track of all the objects that need to be updated. To achieve this, I created an array of objects in the loop constructor function mentioned earlier. I call this array Updatables, and you can see it initialized in the constructor method of the loop class here. Back in the tick method, you can see how we use a for loop to initiate the tick method in each object in this array. Of course, this assumes that each object we created has such a function. In this decentralized or distributed design, each object we want to animate must have a compatible tick method that specifies the direction and speed of its movement. And, if we go back to the code we used to create these objects, say in cube.js for example, you'll notice there's actually a function, called tick, already there that moves the cube a set amount for each frame. The code for that looks like this. In fact, if you look in the modules we use to define each of the shapes, you'll find an equivalent tick method. The final step in this sequence actually occurs in world.js where we first created this cube using the createCube function. Once this object has been created, it must be added to the Updatables array in the loop object we created within our 3D world. We did each of these steps using code that looks like this. With that last step, we now have a logical organization to efficiently construct and animate all the objects in our scene. However, there is one additional feature of Loop.js that we still need to consider. So far, we have ignored the possibility that our animation will need to run on something other than a regular monitor whose screen refreshes 60 times per second. We haven't considered the possibility that a user might run our animation on a super fast gaming computer with a monitor that runs at 240 frames per second or on a modern iPhone running at 120 Hz. Equally possible is that somebody might try to load your animation on legacy hardware that lacks the processing power to support 60 frames per second. These possibilities mean that to achieve a consistent appearance on all devices, no matter how fast or slow they may be, it is necessary to decouple the animation speed from the device's frame rate. One way to do this is by scaling the size of each incremental movement by how long the previous frame took. We'll look at how to do that next. Within Three.js, there's a special clock class that aids in decoupling animation speed from frame rate. The code for this clock class is pulled into our project at the top of Loop.js. Under the hood, this class leverages various web APIs to return an accurate timestamp in milliseconds. In simple terms, the object created with this code is just a stopwatch that measures how long the previous frame took. Within this class, one particular method called clock.getDelta is used to access this value. When you read out this value while an animation is running, you will notice that the delta time for each frame is slightly different. Some frames render a little fast, and others render a little slow. This is normal. And these slight differences are insignificant in terms of animation smoothness. For the same reason, it doesn't matter that this measurement is actually made one frame behind the current one. Once you have this time increment, you can use it to dynamically scale the animation speed. You can see how I do that in the tick method associated with each shape. Here in cube.js, for example, you can see where the delta value is pulled in from the clock object and used to scale movement size based on the frame interval. For this to work efficiently, clocks.getDelta should run once, and only once, at the beginning of each new frame calculation. Then the absolute movement change for each object should be calculated based on this delta. This is done in the module for each shape with the same delta value passed in as a parameter in each case. So far, our example shows two ways of rendering scenes in Three.js. Renderer.render for static scenes and renderer.setAnimationLoop for animated worlds. Which one or which combinations of these you choose to use very much depends on your project goals. Looping animations like the one we've used in this video is the simplest way to build animation into a Three.js scene, but it isn't necessarily the most efficient. It can also be a drain on system resources. Moreover, continuous animation loops aren't necessary for all scenes, some of which don't require constant updating. In scenes like those, you can use a different strategy called rendering on demand, which only updates the scene in response to user interaction. This would definitely be more efficient but harder to implement and deserves a video of its own. Basically, all Three.js projects involve making intelligent design decisions about when and where to use renderer.render versus when to use setAnimationLoop. When developing animations in Three.js, it's always necessary to consider the processing budget and whether or not you are constructing and rendering each frame quickly enough to display a smooth animation. With this in mind, it's helpful to get a readout of the current frame rate at different stages in development. Three.js has a built-in performance monitor explicitly for this purpose. It enables you to track the frame rate in your project in real time. You can see this monitor in action in the top left corner of this animation. That monitor is showing that this hype project was rendering at 60 frames per second, which is what I wanted, although I do notice a few dropped frames. This monitor is contained in the stats.js module that ships with the larger Three.js package. Returning to our project structure, you can see this module isn't part of the core Three.js package. Instead, we need to add it separately by adding the stats.js file to the hype resources pane and then pulling that code into a module I've called monitor.js. You can check out the exact specifics of this process by examining the example code accompanying this video. And that's it for our example of animating a Three.js scene. I hope you enjoyed this fourth introductory video and better understand the power of using ES6 modules and Three.js together in hype, and in particular, how to use them to construct an animation loop. I'm sure that you could probably construct a more straightforward animation example, but my goal here has been to describe an approach that scales as your project grows. Arranging things this way helps you better organize your code and future-proofs your Three.js projects. As with past videos that have used the Three.js library in hype, it is important to remember that to use any of these modules, you need to extract them out of the dense directory structure of the Three.js codebase and place them in hype's resources panel. Because hype has a flat directory structure, you should also check that any file references inside these modules reflect their new location. If you're interested to learn more about using the Three.js library in your Hive projects, keep an eye out for future videos on the Altered Mindware YouTube channel.